Hello and welcome back to Start Learning Reals. And as always, I want to thank all the nice people that support this channel on Steady or PayPal. Now today in part 2 we will talk about the axioms of the real numbers. And afterwards in the next video we will finally do the explicit construction. In order to make this work we will universally use the absolute value. We discussed it in the last video and I also told you that we use it to measure distances. And the notation is just given by 2 bars around a rational number. Now one important property you can easily prove is just that it is compatible with the multiplication. Or to put it in other words, you can just pull out the multiplication sign. And for this property the mathematician just says the absolute value is multiplicative. Then the next question would be, what happens with the other operation? Here we can also pull out the addition, but then in general we just get an inequality. And for this the mathematician would say the absolute value fulfills the triangle inequality. And the reason why it is called triangle inequality we will just see later. Of course the important part here is that we still have an estimate when we measure distances. Furthermore, please also recall that we discussed Cauchy sequences in the last video. A sequence of numbers we call xn is called a Cauchy sequence if for all epsilon greater than 0 there exists an index capital N such that for all other indices nm greater than n we have that the distance between sequence members is less than epsilon. To put it in other words, the sequence members lie arbitrarily close eventually. Now you might already know that this looks similar to the notion of a convergent sequence. In this case we have a fixed number to which the sequence members get arbitrarily close eventually. So let's call this number a, and then we know it exists in A such that for each epsilon greater than 0 there exists an index n such that for all indices n greater than n we have that the distance xn to A is less than epsilon. Of course in this case the number a is called the limit of the sequence. Later on we will talk more about the properties of such a limit. But now to get a visualization, let's look at the number line again. For example, a could be here. Then for a given epsilon we would have a minus epsilon here and a plus epsilon on the right hand side. And now we have here a nice region around a where each number in this region has a distance from a less than epsilon. Therefore, this region is called the epsilon neighborhood of A. Now, the convergence property here guarantees that eventually all the sequence members lie in this epsilon neighborhood. For example, the sequence could start here, then we have some members here and here and here, but then we have xn here. So this is x with capital N. And then all points that come afterwards lie inside our interval here. Hence only finitely many points can lie outside. However, that's not all. This whole thing works no matter how small we choose the epsilon at the beginning. The only thing that changes is how big the capital N has to be. Okay, with this let's look at an example. Indeed, the first example one sees most of the time is the sequence 1 over n. Here you should see the sequence members get closer and closer to the number 0. Okay, I think that should be clear, and if you want to see a proof in a formal way, we will do this later. Because now I want to talk about an important fact. So what is the relation between Cauchy sequences and convergent sequences? So you see, both definitions look almost the same, and even in the picture they would look indeed the same. The only difference is that in the case of a Cauchy sequence we don't have the point A here given. Therefore the formulation is easier in this case, because we don't need the point A. Therefore, we have the implication from the right hand side to the left hand side. A convergent sequence is always a Cauchy sequence. But not the other way around, the implication from left to right is only correct in R. In other words, the real numbers have a very nice property the rational numbers miss. However, the other implication is correct in Q, so we can prove it now. The thing we can use here is of course the triangle inequality for the absolute value. So for a Cauchy sequence we have to consider this expression, however for the convergent sequence we need to consider this expression. Of course, this is no problem for us, we can just add and subtract a here. And now comes in the triangle inequality. So this simply means here we can pull out the addition. And with this we have established the connection between the convergence sequence and the Cauchy sequence. So of course, this is the whole idea, but now we can formulate the formal proof. So first let's fix a sequence xn, which should be convergent, and let's fix the limit as a. Then we know we want to show the Cauchy property for all epsilon, so let's take an arbitrary epsilon. However, now I want to define another epsilon called epsilon prime. So 2 times epsilon prime should be our original epsilon, therefore we define it as epsilon half. Okay, at this point you should already see that this definition is useful because we already know that in this expression we will add 2 epsilons. Therefore, often in such proofs, a definition in this way only makes sense after you have done all the calculations. Okay, now we can use that the sequence xn is convergent, so we know there is a capital N, such that for all indices greater than n, we know the distance xn to a is less than epsilon prime. So here we use the epsilon prime, because then we can make the conclusion we want. Namely, we now can consider 2 indices that are both greater than the capital N, and then we just calculate the distance between both sequence members. Obviously, now we want to use our calculation from above. And now by assumption for the indices, we know this is less than epsilon prime, and this is less than epsilon prime. So both things together are less than 2 times epsilon prime, which is by our definition just the original epsilon. And with this, we now can put everything together. So for any epsilon greater than 0, we find a capital N, such that for all nm greater than n, we find that the distance between both members is less than epsilon. And that's exactly the definition of a Cauchy sequence. With this, we have proven the implication we wanted to prove. However, for the real numbers, we also want the other implication. And one solution to get this is just to take it as an axiom for the real numbers. So let's call this the axiomatic solution, because here we don't care about the construction. Indeed, that is often the way one starts with the real numbers, because you just have a given rule set with which you can solve your problems. Of course, what we need here is a non-empty set we call R, together with 2 operations addition and multiplication, and an ordering less or equal. Now these things together we call the real numbers if they fulfill all the rules we want. Essentially, we have all the properties we had for the rational numbers plus 1 additional. Okay, so let's list the ones we already know, and I want to start with the rule I call A for addition. It tells us that the set R together with the operation addition and the neutral element 0 is an abelian group. So we have associativity, a neutral element, inverses, and also commutativity. Next we have the same for the multiplication, however now we exclude 0 for the set. In particular 1, which is the neutral element with respect to the multiplication, is not equal to 0. So please keep in mind we just list a set of rules here, and the neutral elements in these 2 assumptions here just get some special names. Of course, the names are chosen in such a way that they fit in with our other number sets. Okay, then the third rule I call D for distributive law. This is the same as always, it just connects multiplication and the addition. So at this point you already know these 3 rules together we call a field. Okay, then next I want to put everything about the order into O. So we have all the properties of an ordering, it's also a total order, and also compatible with the operations plus and times. And in addition, we also have the so-called Archimedean property. So now, because you are very observant, you know all these rules are fulfilled by the rational numbers Q. So you can watch all my videos where I talk about these properties. But of course, you have waited for this, for the last axiom we call the completeness axiom. There we just state that every Cauchy sequence is also a convergent sequence. And of course, the distance is measured with the absolute value, which is defined as for the rational numbers. And with this, you have all the axioms of the real numbers. Of course, the visualization is again given by the number line. However, now it's the full number line without any holes. Okay, then in the next video I show you how we can calculate with all these rules very nicely. And afterwards I show you how we can actually construct this number set. Therefore, I hope I see you there and have a nice day. Bye!